Welcome to the deep dive. You know, when you look at a brilliant red sunset, you aren't actually seeing color. You're feeling the physical geometry of invisible waves.
Yeah, it kind of strips the magic away a little bit. But
Yeah.
honestly, the mechanical reality behind how we see and hear is way more fascinating than magic.
Completely. And so I'm gladly taking the student seat today to your lecturer role because we are exploring section 5.2 of chapter 5 from Psychology 2E. Our mission is basically understanding how these simple physical properties of light and sound waves dictate your entire sensory experience.
Right, the whole sensory world.
Yeah, so to get my head around the geometry of it all, I try not to picture ocean waves. I think of it more like a slinky being pushed back and forth.
Oh, a Slinky is a perfect mental model for that.
Okay, good, because I was thinking how hard you push it is the amplitude, right? The sheer physical force. And then how tightly those coils bunched together, that's the frequency. Like how many hit a point in 1 second.
Exactly. And that highlights the inverse relationship, which is, the ultimate translation code for your brain. If you stretch that Slinky out, making a longer physical wavelength well, fewer coils pass your hand every second.
Meaning the frequency drops.
Right, exactly. The physical distance between the peaks increases, so the frequency drops, which is measured in hertz, by the way.
Okay, so how does the brain actually decode a stretched out slinky into, say, the color red?
Well, your retinas are lined with these specific receptors that are tuned to catch specific physical lengths of light.
Wait, so they actually physically catch them?
Basically, yeah. When a long stretched out wave hits the eye, it physically triggers receptors that send a red alert to the visual cortex. And as the waves get tighter and shorter, they trigger different receptors.
Moving you through the classic ROYGBIV spectrum, right? Like greens, blues, and finally violets.
You got it.
And the amplitude, how hard that slinky was pushed, that just translates to how intensely bright that color appears to us.
Yeah, the sheer physical energy of the wave dictates the brightness. But the really humbling part of the test book is just how incredibly narrow our biological tuning actually is.
Oh, yeah. Section 5.2 points out our visible spectrum is unbelievably tiny. I mean, we only process wavelengths between 380 and 740 nanometers.
Which is practically nothing.
Right. A nanometer is a billionth of a meter. We are virtually blind to the rest of the universe's light waves. I mean, honeybees are flying around right now seeing ultraviolet light.
Yeah, and some snakes have biological sensors for infrared.
Exactly. They are navigating a physical reality that's completely invisible to us, which, well, it makes you wonder if our ears are just as oblivious. Do the exact same rules apply to sound?
They absolutely do. I mean, hearing operates on the exact same geometric principles, just interpreting mechanical sound waves instead of electromagnetic ones.
Okay, so for sound, frequency equals pitch.
Yes. Tightly coiled, high-frequency waves physically vibrate the microscopic structures in your ear faster, which creates a high-pitched sound.
And human hearing taps out at around 20,000 hertz, which, sounds really high until you read that beluga whales are out in the ocean hearing up to 123,000 hertz.
It really shows that we live in a very quiet, muffled sliver of the auditory world. And just like with light, the amplitude of a sound wave dictates its intensity.
Meaning the volume, right, measured in decibels.
Exactly.
Let's make that real for a second for the listener. If you're listening to this deep dive right now with your earbuds turned all the way up, you are blasting about 105 decibels of physical force directly into your eardrum.
Which is super dangerous.
The textbook says in just 15 minutes, the sheer pressure of those waves could cause permanent cellular damage.
Yeah, it's literal physical trauma. You're basically bombarding delicate sensory organs with aggressive physical geometry.
Okay, but wait. If frequency is pitch and amplitude is volume, why do a piano and a guitar playing the exact same note at the exact same volume sound completely different?
That is where we get to timbre. Yeah, timbre. It's the purity of the sound. An acoustic instrument doesn't just push out one clean mathematical wave.
Right, because there's the wood, the strings, the body of the instrument.
Exactly. All those elements create a messy, complex interplay of secondary frequencies and amplitudes.
So it's not a single wave hitting you at all, it's a whole chaotic cluster of them vibrating together.
Yes, and your brain is this supercomputer instantly decoding that cluster's unique sonic fingerprint, distinguishing the mechanical vibration of a piano string from the strum of a guitar.
Wow. So when you strip it all back, every vibrant painting you admire and every guitar solo that gives you chills is ultimately just your brain rapidly decoding the height, length, and purity of physical waves.
It really reframes your entire relationship with your own body, doesn't it?
It really does. And
Yeah.
since human biology only allows you to detect a microscopic fraction of the light and sound spectrums vibrating all around us, it leaves you with a wild thought.
Yeah.
What completely invisible, silent wave activity is crashing into you at this very moment?